Dear Professor and classmate, I will present the final report of our team project. We have completed all processing of designing, manufacturing, and testing the pressure sensor. Now, I will introduce these four aspects one by one. In order to design a sensor with a better performance, we simulated with console software to determine the expected change in displacement, stress, and strain of the sensor field under different pressure. From the table, we can see that as the pressure increases, the three indicators increase linearly. We use chromium for metal deposition to make resistors. Therefore, based on the metal pattern we designed, we performed the theoretical calculation to determine the theoretical resistance volume and the required deposition thickness. According to the calculation result, we can see that the four resistance volumes are equal and the design meeting the requirement. As shown in the figure, we have also calculated the theoretical output voltage accordingly. The next step is to design the mask, which is the key to the experiment. The open window mask is used to define the size and field thickness of the sensor. The metal pattern is used to define the metal sensor, and the backside pattern is used to etching the back to form a field. Through the etching of the open window, it's easy to separate the four devices. The yellow area will not transmit ultraviolet light, while the back area will transmit UV light, which will change the property of photoresist and can be removed by the developer. Next, we will introduce the production of sensor and housing. We use primary solution RCA1 and RCA2 for cleaning, in order to prevent unnecessary etching of the silicon wafer, its oxidant. Then the first photolithography is performed to curve the pattern onto the wafer, and then TMAH etching is performed to curve the pattern onto the wafer. The thickness of the field is determined. We etched for hours and minutes based on the etching rate. The expected thickness was 50 micron, and the surface profile shows that the thickness was basically micron, which has close to the expected result. Next, the second oxidation is performed, and then the metal deposition on the front is performed. We set the parameter according to the deposition rate, and the deposition thickness is about 200 nanometer. Through the second photolithography and metal etching, we get a sensor pattern. After removing the PR, we measure the resistance of the two wafers. Since the deposition time of the two wafers was different, their resistance was different. The third photolithography, our goal is to etching the backside to create a thin film. After the oxide layer is removed and the PR is removed, we perform the silicon etching. Due to the thicker thickness, our etching time was also long. The first wafer was etching about 468 micron, and the thin film was about 50 micron. The thickness of the second film was checked under a microscope, and according to the calculation, the film thickness was approximately 35 micron. To test the pressure sensor, the housing needs to be designed to firmly fix the sensor and make sure the pressure was applied currently to the diagram. We made the housing as shown in the picture. The protruding part is used to connect the tray key, and the top hole is used to fix the sensor. Next, we make wire connection and resistance measurements to prevent the wire from moving and causing resistance change. We use type to fix them. The picture shows the platform for measuring sensor performance and how the lines are connected. We test the output voltage generated by applying different pressure, as can be seen from the figure. The output pressure and the voltage are in a linear relationship. We test the data obtained with and without the amplifier, as can be seen from the figure. Without the amplifier, the output voltage is very small. Well, after using the amplifier, the voltage has a vastly difference under different pressure. We also test the output voltage of the amplifier at different step size. Although the step size were different, the output voltage was basically the same. Next, come to test and wiring diagram of wireless system. The following is our code writing and the test video. It can be seen that the test result meets the requirements. The figure shows a specific connection string of the wireless system. The signal is generated by the pressure sensor. The correct data is transmitted to the computer via the serial port, while charting tool can be used to display pressure change. The following is a video of our testing process. In the right picture, you can clearly see the original data. The data after noise filtering, the results are in line with expectation. In this project, we design and fabricate a pressure sensor based on metal stream sensor, including structure design, numerical analysis, manufacturing process, mask design, housing design, and MEMS processing technology practice. During the third photolithography process, because the front side was a metal pattern and the surface was not flat, and the rotation speed was higher when spin coating the back side, and the wafer was not well absorbed and thrown out. So when we made another wafer, we reduced rotation speed and obtain better result. Since the actual conductivity of the chromium during sputtering is slightly different from the theoretical conductivity, and the actual resistance value we measured is somewhat different from the theoretical resistance value. Fortunately, the experimental result matched the simulation result. Through this project, we learn a lot. It deepens our understanding of the design and manufacturing process of MEMS device. In the future, I'll put more effort into study and practice. Thank you.